So we've got rotational kinematics. We've got torque, the rotational analog of a linear force. We've got Newton's second law for rotational motion, and we've got a new type of energy for an object that's rotating, right? Rotational kinetic energy. So the only thing we're missing is our rotational analog for momentum. Okay, so to rigorously derive our expression for angular momentum, we need calculus. Much as I love showing the process through calculus, I do have a couple ways for us to arrive at this expression for what we call angular momentum. Okay, we're going to use the variable L, capital L, for angular momentum, and I'll show you at least algebraically where this expression comes from. We actually have two formulas. So if you remember, we've got Newton's second law for rotational motion, right? So torque is equal to the cross product between the radius vector and the force applied, right? We also have torque is equal to the moment of inertia times its angular acceleration. So we're going to do something similar with the angular momentum. Basically, we're going to have two formulas, two different ways of expressing the angular momentum of an object. If you remember the right-hand rule for torque, you remember that the torque vector was perpendicular to both the radius vector and the force vector. So our angular momentum vector is also going to be perpendicular to two vectors. So I'm going to show you what those two vectors later on, or what those two vectors are later on. So any property that, or any object that's rotating has this property. They do have angular momentum. So just like with linear momentum, in order to change the momentum of an object, we have to provide an impulse, right? We had to apply a force over some time interval. So now we also have to get something rotating, right? We have to apply a torque, we have to get something rotating, change its angular momentum, so we will have to apply an angular impulse. So we'll see the similarities between linear momentum and angular momentum, particularly with these two properties. The angular momentum, or the angular impulse momentum theorem, which I'll derive, I have it in the solutions, and the law of conservation of angular momentum. So basically those two concepts we dealt with in linear momentum we're going to define for a rotating object. Okay, so we've got an object in translational motion. It has its traditional kinetic energy, it's got its traditional momentum. Okay, and so now we have those same properties. Okay, the same properties for an object that's rotating. So how do we get this I omega? So I start off with Newton's second law for rotational motion. And so what I'm doing is I'm rewriting alpha as the rate of change of the object's angular velocity with respect to time. So if I write this delta omega as the final angular velocity minus the initial angular velocity, and I distribute this I across. So now I've got this new quantity, right? This I omega. What is this, right? What's this new I omega? Notice how this, the change in this, is related to the torque, right? So I'd like to describe this or define it. So what do? I take the units, right? Take the units of moment of inertia, which is kilogram meter squared, multiply it by the units of angular velocity, radians per second. Again, remember this is kind of like a pseudo unit that can be ignored. I've got a kilogram meter per second in here, right? I got a kilogram meter per second, and then I got another meter, right? So I got an extra meter right here. If I group my kilogram meter per second together, these are my linear momentum units, right? So my angular momentum has units of linear momentum times a distance or a length, right? So it's got a length unit times my momentum unit, and that's going to be handy later on, right? So it's got units of p and units of r, say. Okay. So this I omega we define as angular momentum, and you notice that's usually how we translate from linear components to angular components, is by using that r vector, or using that distance, okay, to convert from rotational to linear and back and forth. Okay, so any object, right, any object whose momentum is changing. So I took this I omega, right, and I am now calling it L. Okay, so this is another form of Newton's second law for rotational motion, that the net torque on an object is its change in angular momentum with respect to time. This, if you multiply both sides of this by delta t, it looks like the impulse momentum theorem for an object that's rotating. So this is my angular impulse momentum theorem. Okay, basically Newton's second law written in terms of momentum for a rotating object. So what if an object's angular momentum isn't changing? Right? If an object's angular momentum isn't changing, that means there's no net torque on the object. Angular momentum is conserved. That means the final angular momentum at some time is equal to the initial angular momentum at some time. Okay. So this, much like we used with collisions, P final is P initial, we have the law of conservation of angular momentum. Okay. So again, we're seeing a lot of similarities between chapter 6 and what we're doing now, right? No net force, no change in momentum. No net torque, no change in angular momentum. Right. So if I have an object rotating with an angular velocity and a moment of inertia, I can calculate its angular momentum. If any of these quantities change, right, and we haven't dealt with the moment of inertia changing, but we're going to handle cases where a system's moment of inertia changes and the angular velocity may or may not change. Okay, so we're going to handle those cases too. So if there's change in any of these two quantities, angular momentum is changing. Okay. So let's start with a conservation of momentum example, right? A pretty straightforward one. We're going to use the law of conservation of momentum to set this problem up and find the new moment of inertia for this carnival ride. So the carnival ride is rotating. It's got an initial angular velocity of 30 RPM. I hate seeing those RPMs, right? You probably do too. But we're going to have to convert them to radians per second, so I'll do that first. It's got a moment of inertia of 55 kilogram meters squared. So that's good. I got a value, right? I don't have to model it as like a disk or a sphere or anything like that. So I just got a straight number for the moment of inertia. That's nice. The arms change position, causing the arms to increase the angular velocity to 45 RPMs. So we see an increase in angular velocity. All right. Now I want to pause for a second and just talk about something that we're going to be doing in lab. All right. So it's not exactly syncing up. It's usually what happens with an accelerated course. But take a minute. If you want to pause the video, if you've been watching videos like crazy, pause the video, go to Pre-Lab 10 and read that pre-lab, and it'll show you how we can actually change an object's moment of inertia, right? If we change how the mass is distributed across an object, we can actually change the moment of inertia, okay? So we can make it larger or smaller depending upon how the mass is distributed. If you think of like a figure skater, right, you wonder how they do the, like they spin and then they go up in the air kind of thing. They're bringing their mass closer to themselves, and they are decreasing their moment of inertia, right, because their mass is closer to their axis of rotation. So that's basically what's happening here. You'll see an example of that in Pre-Lab 10 too. So the arms are going to change position, and I'm expecting a decrease in the moment of inertia. Why am I expecting a decrease in the moment of inertia? Because the angular momentum is increasing. All right, and this is a conservation of angular momentum problem. I don't see any net torques. The object is rotating. I don't see any torques being applied on the object. So with a decrease in the moment of inertia, there's an increase in angular velocity. So let's set it up. Let's use our conservation of angular momentum equation. First, I got a little bit of dirty work here, right? I got to get rid of these revolutions per minute. Okay, so multiply it by 2 pi radians over 1 revolution, multiply it by 1 minute over 60 seconds, and I get a nice angular velocity, pi radians per second. Okay, so that's okay, right? I'm just going to bring pi along. It's no big deal. Maybe it cancels, maybe it stays in my expression. It's all good. I've got an initial moment of inertia. I've got a value. So I'm looking for the new moment of inertia once the arms change their position. So I've got a new angular velocity. I'm doing the same thing, right? I got to convert RPMs to radians per second. So I see an increase, right? I go from pi to 3 pi over 2 radians per second. So I'm setting up my conservation of angular momentum statement. The final angular momentum equals the initial angular momentum. That means the I omega is the same at the end as it was at the beginning. So you see here omega final is going to increase. That means the moment of inertia should decrease, right? Because this is an equation, right? So this statement has to be true. So if omega increases, or omega final increases, I final will have to decrease. So that's what they're asking for. They're asking for I final. I have all 3 of these values. It's pretty nice. The algebra is not too bad. I just got to divide both sides by omega final. Plug everything in. My pi's go away, right? And I've got 55 kilogram meters squared. These cancel, right? Which is good because I want units of rotational inertia. So 55 over 3 halves is 36.67 kilogram meters squared, which is what I expected, right? With an increase in angular velocity, I'm expecting the moment of inertia to decrease. Okay, so it's a nice basic conservation problem here. So we'll do another object that's rotating. Now it's a merry-go-round. So what happens here is we've got an issue here, right? It's not just an object rotating. There's a person on the merry-go-round, and what actually happens is this person is going to move, and when this person's position changes on the merry-go-round, the moment of inertia of this entire system is going to change, and we'll talk about how that happens. So we're going to model this student as a point particle. Okay, we've talked about the moment of inertia of a point particle in an earlier part of this chapter. If I can model something as a point particle, then it has a moment of inertia of just mr squared. Right? It doesn't have a shape, it doesn't have geometry, so I don't have to go back and look at those like special expressions for a shape. Okay, a point particle just has the moment of inertia mr squared. So if this point particle is on the merry-go-round, the total moment of inertia is the sum of the individual rotational inertias of each object. So I'm going to have to write an expression for the moment of inertia for this merry-go-round student system. So I've got the mass of the merry-go-round, I've got the radius of the merry-go-round, and I've got the mass of the student. I have an initial angular speed, right? So here's what happens. Not to confuse you too much here. It says after a student with mass 60 kilograms jumps on the rim of the merry-go-round, the system's angular speed decreases to 2 radians per second. So this is actually the beginning of my problem. All right, so I'm starting my problem with the student on top of the merry-go-round. Okay, so it's on the rim of the merry-go-round, so the student is right here, right on the edge of the merry-go-round. So what happens is the second part of the problem is the student walks towards the edge, or from the edge towards the center of the merry-go-round. So the student's R vector is changing, right? The student's getting closer to the axis of rotation, so the student's R vector is decreasing. Okay, so that's going to cause a change in the system, and we're going to look and see what that change is. Okay, so the student walks to a point half a meter from the center. So it starts out here at the edge of the merry-go-round at 2 meters from the axis, and then it moves towards the center and then stops at half a meter from the center. So we're looking for the new angular speed of the system after the student moves in 1.5 meters. So let's start with part A. Part B is finding the rotational kinetic energy, right? The change in rotational kinetic energy. So I'm just going to calculate the initial and the final rotational kinetic energy of the system, and then we'll see what that change is. Okay. So the first part, I'm going to set it up again like a conservation of angular momentum problem. All right. There's no net torque on the system. The student and the merry-go-round is one system. Okay. So I'm going to treat it as one object, one system, no net torque. So I'm going to say that angular momentum is conserved. I've got the moment of inertia for the merry-go-round. I'm going to model it as a cylinder or a disc, 1/2 mr squared. I have my quantities. Okay, I've got the mass of both the student and the merry-go-round, the radius of the merry-go-round, the initial position of the student, and then the final position of the student. So I have two R vectors, right? I've got an initial and a final position for the student. When the student is at 2 meters, we've got an initial angular velocity of 2 radians per second. I'm looking for omega final. So I'm setting up my conservation of angular momentum problem, just like this. Okay, initial angular momentum equals final angular momentum. So I'm just going to start off with an expression for omega final. Let's just divide both sides by I final first. Okay, so I've got an expression here for omega final, and I'll be ready to plug stuff in once I actually find out what these moments of inertia are, because I already have the initial angular velocity. So I have to write expressions for the moment of inertia for the system before the student walks towards the center and then after the student walks towards the center. So the initial moment of inertia is the moment of inertia of the merry-go-round, which doesn't change, plus the initial moment of inertia of the student. Again, I'm modeling the student as a point particle. It's on the edge of the merry-go-round, so it's mr squared, and so we're going to use that initial position, 2 meters from the center for the student. Okay, so keep an eye out for this. If you've got, this happens very often, you've got a rigid object, you've got a solid object, and then some point particle collides with it, right, or some point particle moves on that rigid object. So we have to write our moment of inertia as the sum of those two objects. So I'm going to cheat a little bit. I'm gonna plug my numbers in right now. Okay, let's plug our numbers in. Right, we got our masses. We've got the 2 radii right here. Okay, or the two positions. Right, we got the radius of the disk. We got the position of the student. Plug it in there. We got a nice number, 440 kilogram meters. The only thing that changes here, right, in order to write I final, the only thing that changes here is the position of the student. So the student changes position from 2 meters to 0.5 meters. Okay, got another typo there. Sorry. That should be a final. That should be an F right there. So the position of the student changes. Position of the student changes. The moment of inertia of the merry-go-round stays the same. Okay, moment of inertia of the merry-go-round stays the same. It's the moment of inertia of the student that's changing. So the moment of inertia of the student is actually decreasing. You see that? This number decreases. So we see the total rotational inertia of the system decreases. Which again, going back to that figure skater analogy, the figure skater brings their mass closer to their axis of rotation, which causes their moment of inertia to decrease and their angular velocity to increase. Okay, that's why we see them speed up as they spin and launch themselves from the air. So we have a decrease in moment of inertia. We've got a new one, 215 kilogram meters squared. Plug everything in. We've got a new angular velocity, which is larger than the initial angular velocity. That's good. Again, that's what we're expecting. Okay. Moment of inertia decreases due to the student walking towards the center. Angular velocity increases. Okay. So again, like I said, watch out for this. Right? If you have, sometimes you might see a disc with like a piece of putty get dropped on it or something like that. You just add the point particle's moment of inertia to the moment of inertia of that solid object that's rotating. So the second part was find the change in rotational kinetic energy. Fortunately for us, we already calculated the initial and the final moment of inertia. So we're just going to use these numbers for I final and I initial. So the change in kinetic energy, the change in rotational kinetic energy is the final rotational kinetic energy minus the initial rotational kinetic energy. Our expressions for that are 1/2 I omega squared. So all I'm doing is I'm looking for the change. Okay. If you wanted to factor out a 1/2 or whatever, it doesn't help too much, but you could do that. So we have all these numbers now from the first part, right? We have our change in moment of inertia, our change in angular velocity. We can plug everything else in, and we actually get positive, right? We get a positive kinetic energy. So the kinetic energy of the system is actually increasing as the moment of inertia decreases. Okay. Okay. So here we have another problem which is kind of similar. We've got a door which we're going to model as like a solid beam or a solid rod. So this has a moment of inertia, okay, and a bullet hits the door, okay, bullet hits the door, and the door is stationary, okay, the door is stationary, the bullet hits the door, okay, and then the door we presume is going to swing open, right, so this is a collision, right, this is an inelastic collision, and so the door is going to swing due to being hit by the bullet. Okay, so we get the mass of the bullet. We've got an initial speed of 1,000 meters per second. We've got the mass of the door, and this problem says that the bullet hits the door 10 centimeters from the side opposite the hinges. So what does that mean? The door is 1 meter wide. Okay, so that means the distance from here, from the hinge to the edge of the door, is 1 meter. So that means the bullet is actually hitting the door 0.9 meters from the hinge. Okay, so it's not directly hitting it on the edge, it's hitting it 0.9 meters. Okay, and I think what I probably did, I'll look at my solutions again. I think I modeled it such that the bullet hit the edge. So if that's how I did it, I'll go back and I'll make that correction. But it's just a slight modification. We would just have to change the position of the bullet when it hits. Okay. So before it hits the door, does the bullet have angular momentum relative to the door's axis of rotation? That got cut off. There we go. Axis of rotation. So that's part A. Part B, at what angular speed does the door swing open with immediately after the collision? Okay. So again, we're going to model the door as a solid beam, a solid rod, okay, and it's going to be rotating from its end, from the end, okay. So first, I want to talk about that first part, okay? Does the bullet have angular momentum with respect to, relative to the door's axis of rotation? The answer is yes. Just because this object, okay, just because this object is traveling linearly, doesn't mean it doesn't have angular momentum with respect to this hinge, okay? So I'll talk about why that's true in a second. Alright, so let's talk about a point particle, right? If I've got a point particle, the bullet for example, okay, it's got a moment of inertia mr squared. Alright, so if I plug mr squared in for I, okay, I've got mr squared times omega. But omega is v over r, so this bullet has a linear velocity right now. So I can actually substitute v over r in for omega for this bullet. Now what's this r? What does that mean? Okay, we'll talk about that in a second. So I've got mr squared times v over r. One of those r's goes away, and now I have mvr. Okay, I have mvr. Now this isn't a fraction. That's a little vague here. This isn't a fraction. I was just underlining it and showing you that this mv right here, is p. This mv is the linear momentum of that bullet. Right? It's got a mass, it's got a velocity, it's got a linear momentum. So the angular momentum of this bullet is just its linear momentum times its position relative to an axis of rotation. Okay. Now angular momentum is a vector. This is our second expression, or our second formula for an object's angular momentum. Okay. This is very useful for any type of point particle, because if I have a point particle traveling in a straight line, it's got a linear momentum p. And if I pick an axis of rotation, I can measure its position with respect to some preferred pivot point, and I can calculate its angular momentum. So let's go back here to the diagram. It's got a momentum mv in this direction, but it's also a distance r from the hinge. So it's got a linear momentum. It's a distance r from my preferred axis of rotation. So I can describe this bullet in terms of its angular momentum. Okay. So even though something is traveling in a straight line, it still has an angular momentum with respect to some preferred pivot point. Okay, so we've got I omega and we've got r cross p. Right, so both of these are going to be useful. Maybe you'll run into a situation like we did with torque, where you have to set this equal to this. Okay. Now in this case, theta is not 90, right? Because this momentum vector is horizontal, but the r vector is this way. Fortunately, I'm not being asked to calculate the angular momentum. I don't have the straight line distance from the hinge to here, okay, at any given time. But it does have angular momentum. So it's got an angular momentum prior to it striking the door, and that is found by mvr. Okay, so it's r cross p mvr. Okay, so let's set this up. Okay, I've got a 0.005 kilogram bullet. I've got an initial velocity of 1,000 meters per second, and I've got the mass of the door, and the length of the door, I'm going to call it L, is 1 meter. Okay. So this is going to be my r vector if I need it. Okay, it's 1 meter. So I have the door, which is modeled as a solid rod rotating from the end. So I go back to my moment of inertia formula slide, and I see that the moment of inertia for the door is 1/3 its mass times its length, L squared. Okay, it's 1 meter. So the initial angular momentum of the system, I am going to use conservation of angular momentum. Okay, L final is L initial. But I have to find out what the initial angular momentum of the system is. The door is initially stationary. All right, the door is initially stationary, so it has no angular momentum. It's not rotating. It doesn't have a linear velocity, angular velocity, nothing. But the bullet, as we talked about in part A, does have an angular momentum. Okay, and it's got an angular momentum of r cross p, mvr. Now I'm modeling this as the bullet just before it hits the hinge. Alright, so for our purposes, the r vector for the bullet and the p vector of the bullet can be perpendicular. Okay, I don't really care about what's happening before it strikes the door, but the instant it strikes the door, its r vector and p vector are perpendicular. Okay, so this sine theta I don't have to worry about in this case. Okay, so it's just r times p, the magnitudes. And so here's where my my mistake starts to have an impact. Okay, this L would actually be 0.9 meters. Okay, because the bullet doesn't strike directly on the edge. Okay, so as we go through this, basically this number here, I'm just going to have to change to 0.9. Okay, won't have a huge impact on the final angular velocity because there's not much of a difference between those two values. But so that was my oversight right there. So I'm going to just keep explaining the problem as if the bullet hits the edge. Okay, and then in my final calculation, I'll talk about where we should substitute a 0.9. Okay. So the initial angular momentum is just mvl for the bullet. All right. So the bullet has angular momentum before the collision. The door does not. So the final angular momentum, we're going to treat this much like the merry-go-round. We expect after this collision, this inelastic collision, the bullet and the door are going to swing open. Right. It's going to rotate, and so the system is going to have some final angular velocity. Because the system is rotating, I don't want to use that r cross p for the final momentum. I want to use the I omega because it's rotating and it's a rigid object. Okay, so I got to solve for this. Part B is asking for the final angular momentum. What's the final moment of inertia? We've got to rewrite this just like we did with the merry-go-round because it's a solid object and a point particle. So we have to combine those two moments of inertia and write a new I final. Alright, so this is the initial angular momentum here. This is the final angular momentum. This right here is the angular momentum of, or excuse me, that's the moment of inertia for the entire system. Okay, so this is the moment of inertia for the door. This is the moment of inertia for the bullet. Okay, point particle, solid beam, we just add them together. Okay. Now we're ready to solve for omega final, and I think I accidentally put a squared here, so there's another mistake of mine. Sorry, I'm full of them today. So we're going to skip the part where we have to take the square root, right? Because it's just I omega. So solve this for omega final. This will be in my numerator, and this entire expression here will be in my denominator. Okay. So I'm ready to calculate my omega final. Okay. And here's where my first mistake comes into play. This L right here is going to be 0.9. Okay. So this L that we use in our moment of inertia for the bullet is going to be 0.9. So this is 0.9. These two right here, or this is 0.9, that's 0.9, that's 1. Okay. So we're ready to solve for omega final. I'll go back and I will fix this up with all those corrections, and then we'll get an appropriate number for the angular velocity of the system. Okay. So, but everything is, we're still doing conservation of momentum. Just like with the merry-go-round, we've got a new moment of inertia, which is the combination of a solid object and a point particle. Okay, so again, we got to watch out for that. The next problem, we're going to do something very similar. All right, we've got another inelastic collision. All right, but now we have a block that's sliding down a frictionless incline. Okay, and it's a curved path, so I can't use kinematics, right? I don't want to use Newton's laws. So I have to find the speed that this block has before it hits. Okay, I have to find the speed of this block before it hits because I want to treat this like the previous problem, like it's a bullet. All right, so I want to find this block. We're going to model it as a point particle, just like with the bullet. I'm going to find the speed of this block. I'm going to use energy concepts to find the speed of this block. I've got another rigid beam here, okay, and it's going to swing up just like with the bullet and the door. I've got values for everything, right? So the height of this incline is 20 centimeters. The mass of the block is 50 grams. I got centimeters and grams. So I got to convert everything to meters and kilograms. Annoying, but I got to do it. So the uniform rod is 100 grams and it's 40 centimeters long. Okay, so I have L and I've got M for the rod and I've got M for the block. I need V for the block. Okay, so I'm going to set it up like a conservation of momentum problem again, but I've got to use conservation of energy here to find the speed that the block has. Alright, so I've got all my values. I've converted everything. The mass of the block, the height from which the block is dropped, the mass of the rod, the length of the rod. Okay, so we're going to try conservation of angular momentum again. If you notice, it looks very, very similar. Okay, very similar to the previous problem, minus my squared mistake there. Sorry again. So we've got an angular momentum for the block. Okay, it's linear momentum times the distance it is from the axis of rotation. Alright, so just like with the bullet, even though once it slides down the incline and comes off the incline it's traveling in a straight line, it still has an angular momentum with respect to my axis of rotation. Again, just like with the bullet door problem, I've got the moment of inertia for the rod, and then I've got the moment of inertia for the block once it is attached to the rod. Okay, so it's attached to the end of the rod. It's a point particle with moment of inertia ml squared. All right, and so the system is going to have an angular velocity immediately after the collision. So I can solve this for omega final. That's what we're asking for. We can solve for omega final. It's nice one step. Just divide both sides by this whole expression here in parentheses, and I've got this, and I'm ready. But I'm missing the velocity of the block. So I plug everything in. I go, where's the velocity? That's what we were talking about earlier. Okay, we have to use conservation of energy for the block. It's on a frictionless surface. There's no work being done, thankfully, so we can use conservation of energy. So set the initial gravitational potential of the block equal to the final kinetic energy once it leaves the incline. Okay, so I've got my expression for V final. I can plug everything in. Remember, this height is not the length, right? This height right here is not the length of the rod. It's the height from which the block was dropped, which is 20 centimeters. All right, so we plug 20 centimeters in, plug in G, calculate it, and we get something like 1.9, something close to 2. So we get the speed of the block as it strikes the rod. So now I can plug that in here. I've got everything else, right? I've got my lengths, I've got my masses, all that stuff. I can plug this in and calculate it, and I get a final velocity of, or a final angular velocity of 1.4 radians per second squared. Okay. So again, these two problems are very similar. Be prepared for a point particle to collide with a rigid object, and use conservation of momentum to find some property about the system after the collision. Okay, and practice. Okay, practice this. Okay, maybe take a disc with a radius and a mask and have it moving at an angular velocity, and then like drop a rock somewhere, right? Maybe on the edge, maybe halfway between the edge and the center. Practice writing these moments of inertia for a solid object and a point particle combined. Okay. All right, so I think that's it. I'm going to go back and I'll clean this problem up, fix my mistakes, and re-upload it. Anybody has any questions, like I said, I got my office hours in my syllabus, but I'm available. Okay, I've been available. Feel free. Email me any questions. You want to Zoom, we can set up an appointment, something like that. Exam is Friday. That's our final exam. Thanks for everything you guys have been doing. I really do appreciate it. Lots of good exams out there. Lots of communication from you guys. I really appreciate it. I know Physics Online is probably not most people's cup of tea, but you've been doing a great job, so I appreciate it. All right, signing off. Thanks.